Good afternoon, ladies and gentlemen. Good morning to those of you in the US of A. Welcome and thank you for joining us on the first of our 3 sessions around lithium-ion for data centers, mission-critical applications. Today will be an introduction to lithium-ion UPS mission-critical batteries with Nick Shanley. Nick has been with Saft for 5 years, specializing in lithium-ion batteries, 7 years in the standby market. And he's going to tell us all about the values that lithium-ion batteries bring towards your UPS and other mission-critical batteries. We have another 2 webinars coming up over the next 2 weeks. Next week, successful lithium-ion battery integration, and then the week after that, July 23rd, will be all about lithium-ion safety, debunking the risks. For your reference, today we're planning around 40 to 45 minutes. There will be a Q&A session towards the end. Nick thinks he'll be through in about 30 to 35 minutes with his section. So if you have any questions, there is an F&A section. So please just feel free to type your questions in there, and we'll get you some answers on those towards the end of the session. With that, I'd like to introduce you to Nick Shanley, and please have a really nice webinar with us.
Alrighty, thank you, Gareth, for that introduction. Again, my name is Nick Shanley, the sales manager for Saft America, in charge of the Flexion product line for UPS applications. And today we're going to talk, give an introduction to lithium-ion batteries and industrial battery options for the UPS market. So this is a first webinar in our series, as Gareth mentioned. And a little bit about the agenda today. We're going to start with a brief introduction to who Saft is and the main goals of this webinar. Then we're going to take a step back and look at the traditional batteries options that we have today and kind of a 101 review there. We'll switch gears and talk about lithium-ion batteries, generally speaking. Then we'll take a look at why lithium-ion batteries are becoming more popular for UPS applications, and then a brief introduction to our product line for the UPS market, which we call Flexion. So a brief introduction, Saft is a battery manufacturer. We provide solutions from cells to full assembled battery systems. We pride ourselves on being the world leader in advanced battery technologies, over 100 years experience. One of the main ways to be the highest level of, in the market as far as technical solutions, we do a lot of investment into R&D, and you can see here over 12% of our revenue is invested into new technologies. We produce 3 main technologies today: primary lithium, lithium-ion, and nickel-cadmium batteries. We're roughly 800 million revenue. That's our numbers from 2019, and we are part of Total's an oil and gas company, also based in France. We have 4,400 people, 3,000 customers, and 14 manufacturing sites. And Saft as a whole, we actually build batteries for a lot of different applications, from aerospace and defense to data centers, medical equipment, telecom networks, oil and gas market, transportation, and also utility batteries as well. So why are batteries so important for mission critical facilities? And they do play a role in each part of the power stability for the facility. And I would say most importantly, they supply the power to the critical load. And this is for loss of revenue, uptime, business ability, customer satisfaction. So what we're looking at here is you have your critical loads. They're backed up with a UPS. That UPS has a battery inside of it, typically a short duration battery. And then if you go up to the next power level or equipment level, we have switchgear. That's backed up by a station battery as well inside the facility. And then as you have your incoming utility feeds to the facility, you have a substation, which also includes a battery inside. And then last but not least, you have your genset. And obviously you need a starter battery associated with that facility. So all these main applications that provide power to the critical load all has a battery associated to them. And today what we're going to be focusing on obviously is the UPS side, which is one of the most critical applications for the facility. Another thing to mention here is that there's obviously an evolution of batteries and how to use them inside a facility. And so what we're talking about here is using battery as an asset, providing grid services to it, how you can integrate renewables to reduce the carbon footprint for the facility. And also another trend in the data center specifically is putting power at the rack. So utilizing an open compute type of battery system and putting battery power right on the server rack itself. So taking a step back, looking at traditional batteries, firstly, the lead acid battery, this is what we call the flooded or vented type. You can see it has a clear jar where you can see the liquid electrolyte levels inside. There's two main plate types. You have a flat or tubular plate, and a lot of different grid alloys involved with this technology, and where the grid alloy is really designed to add stiffness to the plate structure itself, because lead is obviously a very soft material. We use sulfuric acid here as the electrolyte. It's part of the chemical equation to release energy out. The voltage of this battery is 2 volts per cell. So commonly we have 240 jars to make up the 480 volts UPS. Most importantly, the rundown here, these batteries have a design life ranging from 15 to 20 years, but we typically see the service life of around 8 to 12 years. Maintenance these are pretty high maintenance. They do require topping up, and IEEE recommends quarterly visits to the battery. The main benefit of this technology is that it's a proven technology, roughly 150 years existence. It's widely understood, relatively long life compared to some of the other technologies that are out there. I would say the drawbacks is that these are large batteries, relatively expensive to maintain. They can fail open and unexpectedly. They have cracked jars, plate corrosion, and they're typically designed for the 15-minute runtime. We see a trend in the market to reduce runtimes, so these typically have a little bit longer runtime associated to them, and they are pretty highly affected by high temperature applications as well, where aging occurs faster. The next main type of lead acid battery is the VRLA, or valve regulated lead acid battery. The basics here is it's a sealed maintenance free, where they use a pressure vent cap to recombine the hydrogen and oxygen gases into water to provide watering to the battery itself. There's two main types, gel or AGM, and this is how the battery electrolyte becomes immobilized inside of itself. And there's also a lot of different design types, thin plate, monoblock, multi-cell containers. And for UPS applications, we typically see 40 12-volt jars to make up the battery voltage for the UPS. A little bit about the rundown here. The design life is 5 to 10 years, but we typically see service life around 3 to 5 years. Maintenance on these batteries are relatively high as well. So IEEE recommends quarterly visits. However, they can be monitored with an external system. So that does reduce a lot of the maintenance requirements if you have external monitoring systems associated with them. Main benefits is that they are the lowest initial cost solution. They're widely available, highly recyclable, and very well known in the marketplace. However, the drawback is that short life. Again, they do fail unpredictably, and they have a lot of unique failure modes associated with them, as far as dry out, thermal runaway, negative strap corrosion, positive plate growth, or bulging. So a lot of different failure modes associated with this technology. And finally, just summarizing the traditional batteries is the nickel cadmium battery. The basics here is actually there's a lot of different NiCad batteries available, from pocket plate, which is probably the most traditional and commonly used NiCad battery, to maintenance-free pocket plate, sintered, plastic bonded, foam, and fiber plates. So these are all ways to manufacture the active materials into the plate groups that we know and use today. They have about 100 years experience for this technology. The electrolyte we use is a basic solution, so it's potassium hydroxide. It acts as a preservative, and it's just there to transfer the ions inside the batteries. It's not there to it's not part of the chemical equation to get energy out like the lead acid battery. So it's really there as a preservative. Voltage for these batteries, 1.2 volts per cell. So we actually need 380 cells to build up a voltage of 480 volts for a UPS. So a lot more cells are required for this particular technology. The rundown here is that the design life equals the service life, and it's over 20 years. I've seen some NiCads still in service that have been 35 years going. They're very robust. They're designed for the toughest applications. If you look at the picture on the right here, it's kind of hard to see, but that metal structure is actually a steel that's perforated to allow the electrolyte to seep into the active material to be part of the chemical equation. So there's a very rigid structure holding the active material inside. It doesn't get out of those pockets, and so that's alludes to the robustness and the tough applications that we can handle with this technology. Main benefits is that they don't have sudden death. They're very tolerant to electrical and mechanical abuse, and they're very good in extreme high temperature applications, and they have a low TCO. However, they do have a high upfront cost compared to the other technologies, and they have the longest return on investment. A little bit about a comparison here. This webinar and presentation would be available for anybody that's on the call. So I won't get into much detail here, but I just want to give a comparison against the lead calcium VRLA solution versus a valve regulated NiCad solution. And if you look at the guaranteed life of most warranty periods, the lead acid batteries really only give a 1-year guarantee versus our NiCads that have a 5-year guarantee life associated with them. And then a little bit more comparison here, and to highlight just the failure modes and the effective temperature of those two technologies, whereas the lead acid batteries can fail open circuit, and the NiCads just have a very gradual capacity loss over its life. And then as far as high temperature goes, if you increase the temperature above 25 degrees, 6.5 degrees Celsius, you're essentially cutting the life in half of a lead acid battery, versus you're basically still at 80% of what you would expect the life to be with a nickel cadmium battery. So much more resilient to high temperature applications and maintaining its long life. So moving forward to lithium ion technologies, a little bit about, let's say, the key milestones in history here. In 1976, which is right around the same time the VRLA battery was introduced, few Exxon researchers described the process of intercalation, which is how lithium-ion batteries are stored. And these two gentlemen, good enough, actually won the Nobel Peace Prize, I think last year, as being one of the founding developers of lithium-ion technology. And he's still pretty well involved with lithium-ion even today. 1991, Sony introduced the first cell, the 18650. This is a commonly used cell. It's a little bit bigger than a AA battery, and the nomenclature of 18650 means it's an 18 millimeter diameter by 650 millimeters long, and it's still commonly used today. Sony, however, has, let's say, sold all the battery activities they had to Panasonic, so they're no longer a producer of lithium-ion batteries today. Saft introduced its first cell about a year after Sony, so in 1992, and we've been doing large format cells since 1994. In 2018, the EU Battery Alliance launched, and Saft was a key partner for that committee. That really incorporates, let's say, technology, recycling, and giving the European market a new way to develop technologies for battery technologies. And 2020, so this year, we started a joint venture with PSA Group, which is Peugeot, a major car manufacturer. So we actually broke ground on a gigafactory through the joint venture this year. And in 2025 is when we envision solid state batteries becoming available. So a little bit more about lithium ion. It's actually an umbrella of chemistries. This chart is showing the various of voltages and capacities that are available inside the lithium ion technologies. But on the positive material, we actually have two main types, what we call metal oxides and then the phosphate families. And then on the negative, we typically use graphite or other carbons or a lithium titanate. And then the other thing to mention here is below this shaded blue region is where the SEI layer forms, which is the solid electrolyte interface level. And that's just formed to protect the graphite against the electrolyte during the first charge of the battery system. So it's basically a safety feature inside the chemistry. But if you look at how this chart works, if you want to design a high voltage cell, you could pick something like graphite and MNO as an example and get a high voltage cell, something around 4 volts per cell, or choose an LTO with an LFP chemistry and get roughly 1.9 volts per cell. So that would be a low voltage cell. So that's kind of how this chart works. You could pick and choose different ones for different applications, and there's always going to be a trade-off, which we'll talk about when choosing these chemistries and elements. So speaking of trade-offs, these are the 4 main types we see in the industrial market: LMO, which is a magnesium oxide; LFP, which is a phosphate; NMC, which is a nickel magnesium cobalt; and NCA, which is a nickel cobalt aluminum technology. And the way what we're looking at here is a spider chart. So the further you are out on this chart, the better the attribute is. And we're comparing calendar life, power density, energy density, and the effective temperature. So depending on the application, you can choose a particular technology or chemistry for that given requirement. If you have a high temperature application, for example, maybe you're looking at an NCA or an NMC cell. If you need something that has a high level of safety, maybe LFP is the best choice for that particular application. And then our Ragone chart. So this is really a scale showing energy density on the horizontal scale and power density on the vertical scale. And now what we're bringing back into the picture is where does the lithium ion families fit against your standard lead acid, which is this pink one, the nickel cadmium batteries, nickel metal hydride. I even have silver zinc batteries on here, then the family of lithium ion batteries. So there's actually a wide range of where these can kind of fit. The other thing I put in here in the light turquoise color is an iron phosphate cell. So you can see it kind of just falls right below the metal oxide ones, which are the darker blue lines. And then a couple other things to mention here is that as you go out on the horizontal scale, which is being pushed mainly by the automotive market to get more miles per charge, that's the idea for what's being pushed at and looked at today as far as how to get more energy dense inside the batteries itself. To kind of give you another scale of reference here is that gasoline is something like 2,000 watt hours per kilogram. So we're not quite at the same level there, but this axis is definitely getting pushed out, mainly driven by the automotive market. And how you produce a lithium ion cell, there's 3 main types or cell formats. We have cylindrical, prismatic, and pouch. And how we design or build a battery, typically you start with a mandrel, which is shown on the right here. And then we have foil groups of either copper or aluminum foil with active materials printed on them, almost like an inkjet printing machine. And then they're wrapped around the mandrel with separators to form what we call the jelly roll. Then the jelly roll gets put inside the rigid aluminum jar. In this case, it would be a cylindrical one. The cylindrical is very good for cycling applications, for expansion and contraction, very good for high capacity levels per cell. However, most modules or cabinet designs are rectangular. So as you can envision having circles inside of a rectangle, you lose energy density. So you have area that's not being consumed by active material, the lithium ion batteries. So these are relatively lower energy density compared to some of the other cell formats that are available. Prismatic is very similar to cylindrical, but obviously it's a more rectangular jar, so it's much better to do energy dense applications. However, when you pack them close together, you definitely have to take a look at the thermal design and to ensure that none of the cells would affect the module in case of a thermal runaway going on inside the cell. And lastly, pouch, which is very similar to prismatic. However, we use a foil container, not a rigid aluminum jar. And then what we say here is that it's somewhat difficult to seal for long life applications. And then the other thing to mention on cell formats is that we can actually vary that winding process that I mentioned for the jelly roll and get different performance characteristics out of the battery. So if you have a tight winding with, let's say, less active material inside, you have more surface area. That means you have a higher power battery versus adding, let's say, higher level coating, less turns on the jelly roll, you can design higher energy battery in the same exact cell format. A little bit about safety. It's very difficult to have a discussion about lithium ion and not bring up the topic of safety. However, just to reiterate, our third webinar is going to be a really high deep dive onto this topic, but this slide is really a nice way to give end users and to kind of demonstrate our philosophy on safety for designing a system. And what it is, it's a holistic approach looking at material and process control at the factory, so how you deal with quality, contamination of particles, and so on, choosing the right chemistry for the application, how is the cell designed, how do you deal with venting or current interruption at the cell level, and then finally the system design, the electronics, software, mechanical, all those things. So all these things equals, if you can design each of these pillars, you essentially have a safe lithium-ion battery system. And then what is a BMS? BMS is a battery management system that's required for lithium-ion batteries. But what I'm showing here in the top left is what any BMS should protect against the main safety functions. So your BMS should protect against overcurrent, so making sure that the battery strings are not overloaded. It should protect against over temperature. So if you have thermal sensors, thermocouples inside the battery, if any of the modules are getting too hot, it should protect against that and isolate that particular system or string. Over voltage, and that's checking each individual cell. And then finally over discharge. And over discharge is not necessarily a safety event, but you have to be careful if the battery stays at a low state of charge for a long time if you were to go to recharge it. So that's why it's a main safety function. But how we do that is through measurement and detection devices. It also performs cell balancing. We have switches, contactors, circuit breakers, MOSFETs inside the system, all safety algorithms that look at all the information going on and computing calculations like state of health or state of charge. The alarm management, so how the alarms are raised to the customer, all that incorporates a layered approach of safety through the BMS. And then on the right side of this slide, what we're looking at here is some of the information that you can get from the BMS. So we're looking at cell voltages, min and max, temperatures, again, min and max, how much available current is there, how much available current you can recharge the battery with, what is the state of health, what is the state of charge. Just a little bit here, state of charge is really just a sense of what voltage the battery is at, where state of health is, how much aging has the battery gone through. So there's algorithms in place. Knowing the chemistry in great detail helps you calculate these parameters. And then obviously all the warnings, how many batteries are connected, all this information is available from a lithium-ion battery. And then just a quick overview and tying in some of the other technologies. Again, I'll look at a few key things. Again, just to summarize the energy density, looking at lead acid versus, let's say, a phosphate battery, you're looking at 30 to 50 watt hours per kilogram versus 90 to 120 for a phosphate lithium-ion battery. Charge time, very important for some customers to get the uptime back to the system. typically you're at 8 to 24 hours for a lead acid battery versus a phosphate battery that's typically done in about 1 or 2 hours. So much faster recharge on these lithium-ion batteries compared to lead acid or nickel cadmium batteries as well. So we're going to change gears now, focus on the UPS application, and mainly what we're looking at is the data center in particular. And for this, we kind of said, okay, well, what's important for a data center? And we said the battery should have long life, as it should last as long as the equipment. These should be safe. These are going indoor, inside man facilities. They need to be compact. Real estate costs keep going up. Saving space saves money. They should be easy to own and operate, maintain. And here we're looking at TCO, preventative maintenance, ease of installation, and then finally, reliability and availability. And we know that these batteries always need to provide power to their load. And what we're going to compare here is a lead acid battery and lithium ion, and more particular, the VRLA technology versus a Flexion system. So if you look at the service life, lead acid batteries can obviously fail suddenly. IEEE recommends changing them out once they reach 80% capacity. So here is a graph showing a typical VRLA life versus the Flexion life. You can see it's just a very predictable gradual fade of capacity as it ages. Temperature does affect any technology. The higher the temperature, the shorter the life. So then that would be applicable to VRLA, but also lithium-ion batteries as well. Installation safety. So VRLA batteries, very well-known battery room design criteria. I would say the heat rise during a thermal runaway is less. The likelihood of propagation on an open rack design is a lot less. And then with the addition of a battery monitoring system, it definitely improves, let's say, safety overall. And then if we look at some of the new requirements for lithium-ion batteries, NFPA and IFC have new requirements for battery rooms. So these are pretty well documented now in the latest codes from 2018 and on. They do require now a lot of additional testing, and one of the tests I mentioned here is UL 9540A, which is a large-scale fire test. And that's an evaluation of the system. Again, we'll probably talk more about that in the safety presentation. Heat rise obviously is dependent on the chemistry, the cell, and the module design when you're looking at lithium-ion batteries. And thermal runaway is more critical in prismatic cells because of the tight configuration. BMS, the monitoring system or management system, is included here. So it lets you know if there's any issues going on with the battery technology. Footprint, looking at a 1 megawatt example. This is a VRLA typical 40-inch cabinet. You have 5 of them to build the power up to 1 megawatt versus our Flexion system for Gen 2 would be roughly 6 cabinets here. So if we put them over each other, essentially what we have here is roughly a 50% savings on footprint. So that's a huge savings when you're designing battery rooms. TCO, there's still a premium upfront, let's say, expense to the lithium-ion technology. We say it's in the ballpark of 2x. However, if you look at it from a TCO analysis, it's going to pay for itself after the first change out of the VRLA system. So this was done with a partner actually in Canada, and we can fine-tune this TCO, CapEx, OpEx to any application. It's a nice tool that we have to design for with customers. Finally, reliability and availability. A few definitions here. Firstly, reliability is the mean time between failure of a system, so the MTBF, and the availability is really the amount of uptime, and that typically includes the time to repair. And we know availability is key. There's 2 key functions to add here, is that you can add parallel strings to really improve the reliability, and that's for VRLA or lithium ion. So quick kind of picture here is you can easily add an N+1 configuration, greatly improve the reliability. The other thing now with lithium-ion batteries is what we do is if you have that same design for cabinet requirement for your application, we can actually remove a cabinet, run the simulations, and see what type of runtime you get out of it. So typically, generators can start in 10, 15 seconds, and they're online within 30 seconds. We can see how much runtime you get for that critical changeover of power from the loss of utility feed to your generators to make sure that battery system is well equipped, even if you lose a cabinet. The other thing is that keeping spares on site definitely improves the availability. And what I'm showing here on the right is our spare cabinet, spare module cabinet. So if you wanted modules to be aging with the system that's purchased, you can do that. And these are basically floated in parallel with a little power rectifier on the top of the cabinet, and your spare electronics are seated at the bottom of the cabinet. To summarize, when to consider lithium-ion, it's a lighter technology versus lead-acid battery. You're talking 10 to 20% of the weight savings, smaller footprint, roughly half, much longer life, lower total cost of ownership. It has the integrated supervision, and it requires less maintenance. And here, typically, we see lead-acid batteries requiring annual discharge tests. And for our system, it's really roughly 2 seconds per string to do the maintenance. We have a built-in auto test that typically just checks the internal contactors. It takes about 2 seconds per string to run through that test. Quick introduction to lithium, our product line for UPS. So Flexion, it's a flexible power solution. It's designed for mission critical applications. Everything is done from Saft, from the cells through the full battery installation or battery assembly. We can build batteries from 100 volts to 600 volts with our UL listing, and can go even higher with the CE mark. We can do up to 18 parallel strings to meet a huge range of power and energy requirements. To give an example of that full 18 strings, that's roughly 2.5 megawatts of power under one controller. And then right around the corner for us is our Gen 2 launching, and I'll talk about what that is in a little bit. There's 4 main components of our system. The battery module, it has 14 large format cylindrical cells, a bus bar, and also an SMU card. Then we have our BMM, which is the battery management module, the IntelliConnect, which is really the power box or power connectors of the string. And then finally, when you have multiple strings working together, we have a master BMM that really just acts as a communication gateway for our system. And you can see it has a built-in HMI display as well. So everything is visually available right from the front of the cabinet. Looking at how we designed the battery system from a chemistry point of view, we looked at the application requirements and graded what does a UPS need. And we determined that calendar life, power density, and safety were really the key requirements for the UPS application. And based on that, you can see how LFP really provides zero trade-offs on those attributes that are required from a chemistry standpoint. So we chose an LFP-based chemistry to start our Flexion design system. And when you talk about safety, it's really how, let's say, hot or how the thermal runaway behavior of that particular chemistry is. And what we're showing here is a comparison of a metal oxide NCA cell, which is the red line, versus the yellow, which is our LFP technology. And this is on a log scale, so you can see that the heat rise is roughly an order of magnitude less with the LFP. So it's much, let's say, less risk associated with this technology versus some of the other metal oxide options that are out there. And then a little bit about our BMS. This is where all the safety functions are built into it. The key things that we designed into our system is that it has an internal power supply. So we don't require any external power supply going to our cabinet. The other thing that's, I would say, unique to our product is the IntelliConnect, and this keeps the battery available for discharge. And so if I blow up the schematic here, what we're looking at is the dark blue line is the battery modules, the yellow is the BMM, and the green is the IntelliConnect. You can see the internal power supply is inside the BMM, but we can manage the charge or even stop charging of the UPS through this K1 contactor here, and the battery can still discharge through the diode. So that's just another level of safety for overcharge for our mission critical applications. And then finally, a little bit about our roadmap. There's two main reasons for developing our next gen product. One is to improve safety, and it's really to position ourselves to be best in class in power. We know the market trend is to reduce backup time, reduce cost, drive efficiency with greater performance, and also the gensets are also improving their performance. So the goal here is this year we'll be launching a battery cabinet that can reach 180 kilowatts 4 minutes. That's going to be available around September, October timeframe. And then next year, second half of next year, we'll be introducing a new chemistry that actually gets us up to 200 kW 4 minutes of power per cabinet. The other thing we knew we needed to do is, I would say, somewhat catch up with the codes and standards and to test our system to UL 9548, which is the large scale fire test I mentioned earlier on. And you can see here where we're at. We've already completed our cell level, we've already completed our module level, and our unit level testing, which is the cabinet testing, is slated to be completed with the product launch. The interesting thing about the module level test is that we were able to prove with UL that our modules don't propagate fire cell to cell. So essentially, we can set off a thermal runaway event inside the battery modules, and the rest of the cells are not affected. So that's a huge win and huge signal that everything we're talking about as far as chemistry, cell design, and safety are correlated through UL. So that's a huge win for us on that front. So with that, we can actually open it up for questions. Gareth,
yeah,
you still here?
I have a question. I've got a couple of questions come in.
Great.
Andreas wanted to know what happens if he's unable to attend one of the webinars. How can he get hold of the presentation of that webinar? Simple answer is contact your local Saft person. So either Nick, if you've got his details from the call, myself, or your local Saft person will make sure you get hold of that, any missing presentations from those webinars. Nick, here's a question for you might like to answer. What are the main differences of Flexion versus the Samsung solution? You have LFP, Samsung has NMC. What else is the difference?
Yeah, that's a great question. I would say it's really hard to compare the two, and because they're totally different. Starting with the chemistry, as you mentioned, but then the cell design. So we use a cylindrical cell versus a prismatic cell. Modules, they have two different modules where all of our modules are the same. Ours are kind of front face, rackable. Cabinets are very similar. So I would say it's very hard to compare them side by side, but those are some of the other differences. We have an HMI display. We have data logging built into it. We have the IntelliConnect. So those are the main differences, I would say, in the two products.
I would suggest the calendar life is also different. So the Samsung solution is an NMC LMO mixture. LMO ages more quickly than LFP. So LFP and Flexion itself is designed for a 15 to 20 year product life cycle, and an NMC LMO is going to struggle to get that long. It's more likely to be around about 10 years.
Good point. Good point.
Okay, any more questions? What UPS manufacturers have approved this battery for use with their systems?
So we've tested it with, I would say, over close to 30 at least different UPSs at this point, and they range from how useful it is for them to promote us, I guess, is the one thing, and it ranges on integration. Some of the UPS tests have essentially just tied in an e-stop as far as integration goes, and then some of the other manufacturers have actually looked at integrating full, let's say, Modbus or CAN bus comms into their UPS. But I would say we typically are UPS agnostic. We like to work with anybody that's out there, and we have a running list of tested partners that we've tested with. So we're definitely open to work with anybody on that front.
Okay, the next question ties into that first one a little bit. Is it possible to retrofit an existing lead acid battery when it needs to be replaced with the Flexion without needing to coordinate with the manufacturer of the UPS system, or is it necessary to coordinate with the UPS manufacturer?
Well, I would say I would always recommend coordinating with the UPS manufacturer. Typically, we may need to set the voltage differently. We definitely want to check that out. As you don't want to void it if there's any service contracts or warranty. We don't want to void any of those things out. But I would say we do have a lot of experience doing just that, taking a VRLA or lead acid battery out and putting Flexion in. Because we don't require any external power supplies, we have the IntelliConnect device. This system is very capable of doing just that. But Gareth, I don't know if you wanted to add anything to that as well. You have some experience there.
Sure. Lithium-ion batteries, generally speaking, have a much tighter voltage window than lead acid, so we tend to fit quite well with inside. And the way that the cells and the system are designed, it makes it relatively easy for us to change the voltage. It's a very flexible system, so we can change the voltage at the module level, or even just by reducing the maximum charge values. We have switching circuitry, so we can actually disconnect the charge with a conventional non-intelligent charger. So that kind of stuff is relatively easy to do. And the majority of systems that we do today are retrofitting where lead acid batteries are already in situ.
Yeah, I agree.
Another one. Yes, Andreas, we know that Eaton has approved it for the 9395P and the 93 PM systems. Thank you. What do you think of supercaps? I could take that one if you want, Nick.
Sure. Yeah, you may have more experience than me.
Supercaps, ultracaps, very good, very long life, a lot of power, but absolutely no energy. So if you're really looking for something that's longer than 30 seconds, then you need a lithium-ion battery. If it's shorter than 30 seconds, you can use supercaps or ultracaps. And once you start to get over 30 seconds, the crossover is somewhere between 30 and 60 seconds at the size and cost benefit of supercaps versus lithium-ion. Does Flexion have its own charger, or would it be charged by the UPS system?
It would be charged by the UPS system.
With the exception of the contemporary aging cabinet, which does contain its own charger.
Correct. Good point.
Okay, I don't have any more questions at this time.
Okay, I guess with that, we can conclude webinar number 1.
Unless there's any more questions, give it another 30 seconds.
We really appreciate everybody taking the time this morning, afternoon, or evening, wherever you're located around the world. And hopefully you found this very useful. Feel free to email me any comments, any other further questions you have. And if you want a copy of the presentation as well, we'd be more than happy to send it out. Any other questions coming, Gareth?
No more questions. We can close.
Okay, very good. Thank you, everyone.
Thank you and goodbye, and hope to see you on one of the 2 remaining sessions in the next 2 weeks.